So we're going to be starting our look at solids and liquids. Several pre-AP topics here, so I hope that a lot of this is a memory jog, but we will see. The new hand signal for this, because I have a new person, is a rattler. So that's you're going to see. Make sure you have your slides at home. All right, yeah, you're failing at your one job. I rattled!
You remember your Paul Rudd?
Remind me of Paul Rudd.
Turn into an Ant-Man for me, please.
All right, so our focus today is intermolecular forces. But before we talk about intermolecular forces, can anybody tell me examples of intramolecular forces?
Water. Oh, dipole bonds.
Interesting.
Those are intermolecular. What are examples of intramolecular bonds?
Bonding.
What?
Is it like regular bonds?
So what are they?
Covalent bonds.
Ionic,
Let's go.
covalent, metallic. Really, what we studied in the last unit were intramolecular forces, because those are the bonds that you're used to. Those are the stronger forces that actually hold atoms together. We're taking a step away from that. Intermolecular forces are not the forces that actually build compounds. They're the forces that draw already established molecules towards each other. All right? It's what makes solids and liquids exist, is this idea that after you already have a molecule that's formed using bonds that we've studied, what makes those molecules want to associate with each other? And it's three different types of intermolecular forces that you need to know the science of.
I figured out how to do it.
Intermolecular forces are also referred to as van der Waal, however, not in AP. So you're not going to hear me refer to it as that. I just like to throw it at you in case you come across in college the phrase van der Waal. It's talking about everything I'm about to talk about in this lecture. Now, this slide is an overview, but each IMF has its own slide, so I'm not going to read these to you.
Awesome. I was doing
Okay. So the first thing that I want to touch on is one of the most important things on the connection of IMFs to your FRQs. That was a lot of letters. Phase changes, and you'll notice I gave you the most foundational difference of the three phases of matter that we care about. So there's a review of that if you need those definitions. But changing from one phase to another, all right, is an overcoming of IMFs. One of the biggest trouble areas that you can get into, Robin, stop it, is saying in an FRQ that here's what I've seen or what I've read on student responses. They'll be going through this great thing showing the science of ice melting. All right, and they'll say, and this happens, and then this happens, and then the bonds break. And the moment you write that the bonds break, you're wrong. Because phase changes have nothing to do with bonds forming or breaking. They have everything to do with IMFs either associating or disassociating from each other. It's an overcoming of IMFs, because if I have ice that is a bunch of water molecules that are associated with each other, they're not bonded to each other. They're just attracted to each other. And I pull them apart. Well, in order to do that, that would be melting. But in order to do that, I added energy, so it made them start vibrating faster and moving quicker, and they move further apart. But I didn't break any bonds. I just overcame the intermolecular forces that were holding them together. Yes? Well, there is that creates the water, though, because if I asked you what is ice, you would say that's water. And I said, what kind of bonding is in water? You would say covalent. And you would be right. What I'm saying is for the ice to actually form, for the molecules of water to associate with each other and build a solid structure, it's an IMF, hydrogen bonding in that case, that is creating the solid. If I want to make it become a liquid, I just need to pull apart that IMF. But hydrogen bonds are not bonds, as you'll see in a future slide. I feel like I'm doing this a lot, and I'm sorry.
Well, it's just one group.
Phase diagrams fit really well into here, but AP has not asked a phase diagram question in a very long time. So there's a good chance that you will not see this idea. But it fits here. I'm going to touch on it in case there's a curveball. What this chart does is it plots pressure versus temperature, and it just gives you a substance. You could study any, let me rephrase. All substances have their own phase diagram. And what it does is it's going to plot pressure versus temperature. And what you can see is that at any combination of the two, you can identify what phase that substance would be in. So you could say, okay, well, if I have this type of oil and I want to look at it at 50 degrees Celsius at 10 atmospheres, what phase would it be in? Well, you could go and look at its phase change diagram and just find those points, and it would tell you. The way to read the actual chart is if you pinpoint a coordinate that's not on one of the established lines, then it's existing within a particular phase. You'll notice as you go from left to right on the chart, it goes solid, liquid, gas. So again, if a coordinate landed in one of the open areas, that's just the phase that it's in. But if you find a pressure and temperature combination that lands on a line, well, that would be at equilibrium between two phases. All right, so if I chose, for example, taking you with me. Is that working? I don't know if you can see it at home. But if I chose, for example, this point right here, all right, as my temperature and my pressure here, well, on the line there is in between liquid and gas. Therefore, at those conditions, the sample would be at equilibrium between, well, condensation and evaporation. So I want you to know how to read that. What's that? No. Yes?
So what is that?
Well, of course it means both existing at the same time. Actually, now if you're sitting there wondering, well, what does that look like for them to both exist at the same time? Well, the idea would be that when you looked at it, it would be one or the other, but it would be an average with the other. So if you were to look at the sample at those conditions, you would see one or the other, but you wouldn't be able to guess which before you looked. Does that make sense?
You're kind of like Miss Frisbee, but like snow.
But it would be fluctuating between both. Now, due to the way these graphs are drawn, though, that means there's always a single coordinate that all three phases exist. That's called the triple point, all right? And you can see it's labeled here. Here's the triple point right here for this one, where at that pressure and that volume, it's actually an average of all three phases. That's just a good vocab word to know. Again, I don't anticipate them asking you questions.
So then how is it all three?
In the same way, you just asked the exact same question Diego asked. All right, I'll see if I can find a good video. I know it sounded like a different question. But the idea is that it's at equilibrium at all three. So if I asked you which state of matter it would be in at that point, you wouldn't be able to answer because it could be any of them. It's at equilibrium, so it would be a constant shift, theoretically. Yeah. I'll try. I was shown a cool video in college. I didn't dig anything out, so I'll try to. I don't have a demo for you, unfortunately. So let's go into the 3 IMFs that you need to be aware of for the unit.
It's just so much history all the time.
He just complained that we're doing chemistry.
Every day.
All right, so let's start with London dispersion. This is the weakest of the 3 intermolecular forces, all right, and we're going to get stronger as we go through our list. IMF is going to be the one type of, London dispersion is going to be the one type of IMF that is associated with nonpolar molecules. And here's what happens. Let's say I've got my normal nonpolar molecule. Now, me labeling him as nonpolar is probably going to pull last unit's concepts back into play for your brain. Because if you're given a compound and I want to know which type of IMF is happening, well, if it's nonpolar, it's automatically London dispersion. But you would need to be able to label it as nonpolar. And I taught you how to do that last unit. But let's say that this nonpolar molecule is traveling. Hello. All right? And he strikes a surface randomly. As as he strikes that surface, his shape is momentarily altered. All right? And maybe he flattens up against that surface for a moment. And as that happens, it creates what we refer to as an instantaneous dipole. Just for that moment, as the nonpolar molecule that would not have different charges in different areas, because that's the definition of nonpolar, but as it strikes the surface and it changes shape, this area over here is going to be partially positive because all the electrons are going to get pushed up against that side. And then therefore this side, which all the electrons have traveled away from during that collision, is going to cause a partial positive over there. And for that moment, this nonpolar molecule will have the ability to attract another molecule towards it. All right? Because that's the whole idea, right? It's an electrostatic connection between different molecules that might associate with each other. So for a moment, we've given the nonpolar molecule the ability to attract another molecule towards it. Not bond with it, that's not what we're talking about. This is just a force that can make two established molecules want to go near each other. But then as it floats away, and this is all random, as it floats away, it would retain its normal shape, the partial charges would disappear, and then it would again be a nonpolar molecule that's not attracting anything. This is a very weak force. Now, there is a magical word associated with this idea. And when I say magical word, if you remember like last unit, I was like, if you're describing the ionic character, you have to say lattice energy, or you have to bring up Coulomb, all right? Because that's what they want you to do. If you are describing the science of London dispersion, you have to use the word polarizable, all right? I mean, just think about what it's saying. Polarizable, the whole idea of it momentarily being able to attract something is that it kind of becomes polar for a moment, right? By definition, to be polar means that you have different charges on different sides of yourself. So the more polarizable a nonpolar molecule is, the more it can change shape when it does this random bumping, then the stronger its London dispersion will be. Therefore, one of the conclusions that you can draw is that larger molecules are more polarizable. They've got more electrons, right? The whole idea between creating these partial charges is the electron shifting randomly during this collision. So if you've got a really big nonpolar molecule going through this process, well then it's more polarizable, which means we can change more shape. There's more shape to change for that moment that we're creating these partial charges. I want to point out, this won't be on the AP, but just for your chemistry brain, that polar molecules can do this too, because they're moving around randomly also. It's just polar molecules are exhibiting the other two IMFs, which are stronger than this, so there's not really a reason to even talk about the fact that they do it, but you're going to run into it in college and you're going to think I'm a liar if I don't say it. So, polar molecules also exhibit London dispersion. It's just so small compared to the other intermolecular forces they're exhibiting that who cares? So let's move into polar then. There's two types of IMFs that polar molecules can exhibit. So we'll go with the weaker of those two. All right, now this is automatically stronger than London dispersion now. Yes, and yes, and yes, and yes. Thanks. So let's draw a molecule together to show this. I'm going to draw HCl. What direction is the dipole moment in this molecule? Towards Cl. the result of that dipole moment is going to be a partial negative here and a partial positive here. Are we all together? Now, my polar molecules are always doing this stuff, right? So we don't have to run into something. They're always exhibiting this idea that they've got these partial charges. Therefore, they are going to be able to attract other molecules of themselves in the area just based off charge. Because look what happens if an HCl molecule comes near another HCl molecule. Sorry. Do you see why these two HCl's are going to be pulled near each other? All right? And these partial charges that are opposite, so they love each other, well, they're always there in polar molecules. So now they're going to be pulled near each other. They're not going to bond. None of these are bonds. All right? It's just an attraction that pulls them and will hold them there near each other. This is called dipole-dipole.
Do you still represent these with the 3 dots?
I'm sorry?
Do you still represent these?
We're only until I got asked that question last period, and I want to research it because I'm not 100% sure on the AP answer. Hydrogen bonding, yes, it's the dots. Dipole-dipole, I want to go look because it can't be aligned. So the dots, I want to go verify before I give you an incorrect answer. Yes.
So does it have to be true of the same?
Everything that we're doing when we're looking at this is saying if you've got a molecule, what is its ability to attract another one of itself? All right, that's the ballpark that you're thinking through this. All right. So realize that this could have oriented itself over here also, right? It's just the two chlorines will never orient each other near each other, right? It's going to always orient, as different molecules of HCl come and try to click in, it's always going to orient itself so that the plus is near the minus. I'm sorry? Yes, yes. Will you change the paper before you leave? Just go. The final type of IMF that we'll talk about is hydrogen bonding. The good news is, yes, this is the strongest one. Yeah, no, this is good. This is a lot of communication. I'm glad I'm not teaching. Okay, yes, no, thank you for your help. Hydrogen bonding works in the exact same way. It's not the exact same thing, but it works in the exact same way. So if you have this understanding on polar molecules orienting themselves in this way, then you understand hydrogen bonding. The difference is that for it to be a hydrogen bond, this H has to be attracted to NOF, which is nitrogen, oxygen, or fluorine. Those are the only 3 elements that can create a hydrogen bond is NOF. Have you had a NOF yet? Sounds like the word enough.
Oh, no, wait, really? No, this is
No?
This one got it.
I'm going to be monetizing this one. So let's take a look at water.
No, it's a terrible joke.
I don't know the Michael Jordan.
He jumped him off.
No, stop it. Stop it. We're recording.
Let's talk about the DG.
No. Here we go. So if we take a look at a water molecule, all right, and it is near another water molecule, and I take into account the idea that water is polar, I therefore know that my oxygen is exhibiting a partial negative while my hydrogens are exhibiting a partial positive. So that'll be true for this guy also. So the exact same occurrence is going to take place in regards to this plus loving this minus. But do you see the two elements that are attracted to each other this time? It's a part of NOF. It's oxygen. Let me tell the joke again.
No, it's just the word.
Sounds like a no.
This force is stronger than any other two elements going through this partial charge attraction. And of course, the waters, all of the waters that come in and orient themselves to make a liquid or a solid are going to do so, so that the pluses and the minuses are near one another.
Wait, so when it becomes a gas, is it just still just...
Well, when it becomes a gas, they're completely unassociated with each other. If it's a gas, there's no IMFs occurring.
What do you say it's stronger than what?
If it's the H bonding with NO or F, or I'm sorry, associating with NO or F, then it's a stronger attraction than either of the other two IMFs. Hey, what's that right there that I'm pointing to?
A single bond.
Be more specific. What type of bond is it?
Dipole-dipole.
Ooh, okay, that was key. Y'all went another level. No, it's not a hydrogen bond because hydrogen bonds are not real bonds. What type of bond is that?
London dispersion.
No, London dispersion. It's covalent.
Oh,
It's a bond between two nonmetals. That is a covalent bond. What is the umbrella that covalent bonds fall under? Covalent bonds are type of
The other one,
intramolecular forces. Very good. All right. And then this is a hydrogen bond, which you always show with dots. All right. Which is a type of intermolecular. Which is stronger, the covalent or the hydrogen? The covalent. All right. Because the real bonds are way stronger than any of these IMFs.
How much stronger?
Way stronger. That's what you wanted me to do, right? A multiple choice question waiting for you on your AP 100% revolves around this idea. That the melting and boiling point of substances relies on the type of IMFs that they display. This should make absolute sense to you, considering that on an earlier slide, we said that all phase changes are based on overcoming the IMFs, all right? Pulling them apart into a phase because you added so much energy. Therefore, boiling and melting points, of course, are the phase changes themselves, are going to rely on how attracted these molecules are to each other. In other words, what you're going to be asked to do is if you're given two substances and it just says which one has a higher melting point, what they want you to do is first figure out, well, is it polar or nonpolar? And then after you see that, you can decide what type of IMF is happening. And after you know that, you can rank the IMFs. And if it's stronger, then it's a higher boiling point. If it's a London dispersion, it's a weaker boiling, or I'm sorry, a lower boiling point or melting point.
What do you do if you have
Then they never will be in this class. Her question is, well, what if they're both? What if it's two different molecules that both exhibit dipole-dipole? You're right. There's more science to differentiate those. Never in this class, though. No, I didn't write the AP exam.
oh.
But I
He
do.
created chemistry.
Yeah.
That is a-
Middle
He
color
created
of
it, but he gifted it to others.
So let's take a look at the bottom. The bottom there compares methane to hydroiodic acid. It tells you their polarity, which makes this very simple.
How is CH4 non-polar?
Because CH4 has 4 dipole moments that cancel each other out.
It's an actual bond.
We're comparing molecules to each other.
Yeah. I thought non-polar was only two of the same elements.
It is. So yeah, you're having trouble with. So we've got like chlorine bonded to chlorine, nonpolar because it's two of the same things. All right, but carbon bonded to hydrogen in a tetrahedral form. Even if you go back to your shapes, you know that's nonpolar. All right, because all of these dipole moments are going to cancel each other out.
Oh, I didn't know that.
So it's a nonpolar molecule.
I just took a test.
All right, polar bonds, but a non-polar molecule.
That's what it was, the bonds on.
So between CH4 and HI, which one do you think has a higher boiling point?
HI.
Why HI?
Because it's stronger.
Because it's polar. The moment that we say, well, HI is polar, that means, well, it must be exhibiting either dipole-dipole or hydrogen bonding. If the CH4 is nonpolar, it can only be exhibiting London dispersion. And London dispersion is weaker, therefore a lower boiling point.
So with this question, it's going to be like either, like if we got one that couldn't do any of them, like we have to check for that.
No, if they're asking about boiling point and freezing point, it is an IMF question 100%. So here's what I want you to do. I'm going to give you a few minutes before I start drawing cards. I want you to reflect on this lecture and see if you can answer these questions. Take a few minutes. Sorry? If they are covalent, if they're molecular, then they have the ability to have an ion.
You want to draw the first thingy? Because I don't think I'm going to do it right.
I believe you.
You have to got a chemistry space.
I feel because I'm better than myself.
You're gonna get 100 now. Bless you.
Of course you want.
I'm here for a month of support.
For free.
No one.
Then you're not supporting it.
I'm supporting emotionally myself.
Jacob, can you please pick Jacob to answer all three?
You mean he's got a good chance?
Yeah, because he's a drug dealer.
Are you working on this?
He doesn't
Come on, man.
He said absolutely. I don't think I'm going to draw it right. So
Well, then go to the next one. Just upstairs or the family business.
just see.
Just do your best. They have several resins and isomers, so there's a bunch of ways you can do that. No.
Or you can guess.
None of them can expand. So everything has to fall down.
I don't understand.
Oh, we're doing those are 3 different questions.
So just start with the.
That wouldn't even be.
Yeah, because it's double guess. No. I don't know, actually.
Because I want you to compare the boiling points of the two drawings. It's like it says draw 2 Lewis structures for. You're gonna draw the same one twice? For what? That's all we did last year. Was draw structures for molecules. We didn't draw any crystalline structures last time.
Oh. Do you mean like spreading out? I was thinking really structure like doing the
It's desperate. I'm so disappointed right now.
As you
I didn't refer to those as Lewis structures, so I was confused.
Lewis structure.
I refer to those as like the molecules. Sorry. Oh, I'm so confused.
Damn. Very tired.
Here, I'm not giving you mine.
I'm all out of whack right now. I don't want your periodic table. It's probably ripped up.
No, it
I
has
don't
an,
want it.
it has an
I don't want it.
answer
I don't want it.
from a previous test question.
Okay.
Says
So you're telling me you're cheating?
BE 2 plus. No, it's not cheating. It's from test corrections.
So remember, for those bottom questions, you're asking yourself if that compound were going to associate with itself, what would happen?
I'm not having trouble with that.
Cummings, can you, like, you get the C's and the O's? and
Wait,
just-
so that wouldn't it be the first one then?
That's for the
Oh my god.
Wait, so would it be?
What is that?
What is that? That is
Just
not
trying
right.
to. So wouldn't it be the?
Now this is bullshit.
I don't know about. Yeah. I don't know about those two.
Oh, I didn't want to
Okay,
do
great.
that. Okay.
All I can do is think by the egg.
I didn't draw enough
I wrote
As long as the
London
offset is happy everywhere, then
Wait, so
I feel like the fourth one's a trick question.
would that be hydroxide?
is there a fourth one?
On 30.
No, it won't be right on
Calcium nitrate.
Right.
Nitrite. I know my stuff. Oh my gosh.
I have a question, but I don't want to do it bad.
Here, I'll ask you what you
I know.
Wouldn't that just also be the same as
go.
the ability to
Huh? Where was the point?
I need these options, so I need to.
Like the other two on this class? No, it wasn't right here. Right here. It's just nice.
I was like,
Oh, not right here. What else was it?
No, Roger went to
I'm a silly goose. No.
So what did you age to compare? That's what I need.
You know, the top one is yeah, you're right.
Why didn't you age
Because that's an isomer of this compound.
Oh, yeah.
That's one way that it can orient itself. These aren't resonance structures. These are isomers because the arrangement of atoms are different. I'm not just moving a bond around. It's fine. You're not going to be asked to draw that structure in real life. I just wanted to get. I like it when you sit there and wrestle with it.
Oh, like when I'm stressed?
He likes this.
He likes
Russell.
Here's that made it weird. It wasn't
Yeah, why
weird,
did
and
you-
you tried to make it
Why did you laugh like that?
All right, are we ready to draw some cards?
Sure.
No.
Robin.
Pick Jacob.
He's like, why is he saying that?
Oh, he's. The only time he.
All right, here we go.
Move!
We're gonna first take a look at the first question. All right, so let's go to cluster 3, seat 5. Hey, 3-5. Which has stronger IMFs, nitrogen or water? She said water because you know what I bet she did? I bet she said, well, nitrogen looks like this. And of course, we've already drawn water that looks like this. All right, and we know that this is nonpolar, so it can only have London dispersion. This is polar and actually has the ability to have what type of bonding, or what type of IMF? Hydrogen bonding, not dipole. The water is not dipole-dipole. All right, it's hydrogen. Therefore, this one must have stronger IMFs because it is not exhibiting London dispersion like the other dude is. I'm not going to draw a card. What do you think about my pictures? The question is, which one would have a higher boiling point?
Top one.
Why?
Because the O is on the end, so like these other electrodes.
So he's right. We've got the ability of hydrogen bonding in the top one. And that's actually a more specific answer than you would have had to give because just look at the two molecules in general comparison to each other. Are either of them nonpolar? One of them
Wait, yes,
is.
the bottom.
The
The bottom one is absolutely nonpolar. if you drew all those dipole moments, they would cancel out. I mean, look, it's a completely symmetrical compound, molecule. So I can just look at this bottom one and know that's all London dispersion again, non-polar. This top one, all right, is a polar molecule, so it's immediately going to have the ability to do at least dipole-dipole, but this one will also hydrogen bond. Therefore, the top molecule would have the higher melting point. Let's draw some more cards. All right, let's go to cluster 2, seat 4, Aspen. What do you think about xenon?
I think it's silly. I don't think there's none.
He said none. Do you agree or disagree?
I disagree.
I disagree because it would be a non-metal associating with another non-metal if it's a xenon with a xenon. But hey, look, where did I just say? Xenon with the xenon. That makes them both the same.
Non-polar.
Non-polar, so what type of IMF?
Dipole-dipole.
No!
Dispersion forces.
Is it London dispersion?
London dispersion is the one in non-polar
Oh, I thought it was covalent.
molecules. All right, let's head on over, Faller. Oh no, bad throw. Let's go over to cluster 6, seat 5, Aspen. What do you think about H2S? Quiet. She said hydrogen bonding. Do you agree or disagree?
Disagree.
I disagree. Remember, what we're doing is we're saying H2S coming near an H2S. What will the hydrogens be attracted to? The sulfur. Is H to S a hydrogen bond?
No.
No. It's a dipole-dipole.
Wait,
It's got to be NOF. You can pass Aspen. Let's go over to cluster 5, seat 6. It missed her. Hey, Aspen, what did you get for CLF? She said dipole-dipole. Yeah, I mean, it's definitely polar, and there's no hydrogen, so it can't be hydrogen bonding. It can't be it can't be London dispersion. It must be dipole-dipole. Let's go to cluster 6, seat 2. We're just tearing through Aspen. Riddles. What about the last one? She said she doesn't know. Do you agree or disagree?
Disagree.
It's none.
They disagree. You know.
It's none.
Why is it none?
It's ionic.
Because no one knows.
What is the last one?
It's an intramolecular.
It's the polyatomic in
It's not molecular at all. It's a crystal. Hey, look here. This is important. Do not apply IMFs to ionic compounds.
But it's a.
The only thing that you would describe about forces in a crystal is the phrase lattice energy. You can bring up lattice energy if you're talking about ionic force, but you may never bring up IMFs. Don't get tricked into it. That's a crystal.
I was thinking so hard. I was like, what?